Hello to each and everyone. My name is Karan Gupta, and today I would like to discuss about the abacus analysis. Particularly, the the equipment that we are going to take into account is a medical equipment, that is medical syringes. So, if you want to know more about how I have designed these medical syringes or this particular syringe, then I really motivate you to check it out my SolidWorks tutorial where I told like a bit about how to model all these parts, because in syringes we have generally three parts for a conventional syringe. One of them is a barrel, another is a plunger, and one is a stopper. So how I have designed it, so I have tell you quickly in a brief section there at my SolidWorks tutorial. So please try to check it out. The next screen that you will see is going to be the Abacus screen. So we are already familiar with the user interface of Abacus. Today we will try to learn a bit about different types of materials that we can give, like linear, non-linear materials. For rubber, particularly, we have like thermos, different types of elastomers that we have to define. Even for the soft tissues, we have to use the hyperelastic properties. Also, make sure like this session is mainly consists of the plastic materials as well as the rubber. So for metallic, we have already did some part of it for steels, but for polymers, this is what we are doing it today. So what we have to do, we have to import our geometry. So I have already taken a part of it, so we just simply go to the import assembly, and this is, let's say, the part that I'm looking for. So it asks for all the components, so I say yes. So right now we have like a syringe. uh, it's a quadrant of it. Why we need a quadrant is because we have to reduce the computational power. And what we can do later on also, there is a possibility that we can put on the symmetry. Because of the symmetry we can have the other parts also, but for our use case it's good enough so that we can understand like how much the rubber is going to put a contact pressure, so that we can understand the reaction forces. For example, why we need to do this analysis, there is a very basic question. So we really have to understand like how, what's the purpose of syringes. We have to understand like how much the force we need to push and pull the syringe. That's what, one of the basic understanding that we have to understand. So this analysis will tell like what are the reaction forces needed as per the compliances or as per the human needs. So that's what we will do it today itself. We'll try to understand the reaction forces. This is one of the medical example, but this is what you can put it to other examples also, other medical devices. So as told earlier, if we go to the part, then we have a plunger, then we have stopper, and everything is designed in SolidWorks. So since a part is already being defined, now what we have to do, we have to define the properties. So either you can just check it from this tree section, this drop down stuff, or you can just select it from this module part. So we initially define the barrel as ABS, and we'll try to check it out the elastic properties for it. So it's always within like 1900 MPa, between 2500 MPa. That's the Young's modulus. So let's take it like 2200 MPa is the Young's modulus. Poisson's ratio is 0.3. And now we can define the rubber material. For rubber, make sure like in elastic we have to select the hyperelastic because that's a non-linear elastic material, and we are checking out for Mooney-Rivlin, and we can just put on the coefficients. So I have already taken into account the rubber material. These are some of the coefficients. So like make sure like these type of hyperelastic material itself has a different theory, and one has to really understand this theory, so that what are the different parameters being added here, and what are the constitutive laws and equations that defines this equation. For example, if we talk about the soft tissues biomimicry, then we have the Austin model. So we have to understand all these parameters that we put, like alpha 1, alpha 2, and compressibility factors even. So everything is there. So if you request me, I will try to put on some videos related to that. Okay, so now what we have to do is go to the, so we have defined the property. Now we have to assign it to the section. So let's say one of them is barrel, solid homogeneous part. I select for barrel it is ABS, all fine. Then another one is the plunger. For plunger, we define again as ABS. For stopper, it's going to be the rubber material. So I define rubber. Perfect. Now it's time to assign the section. This is really important. So let's say if I'm assigning section, try to write it down here also for your simplicity. You create all the sets. So select it, give it, and what it is a stopper. Now we want to assign for the plunger. We are going to go to the section, assign. It's a plunger path. So done. Sorry, it's done. Then we have the barrel. So again, assign the section, give it barrel here, and assign it to the barrel. Okay, perfect. So we have defined the section, and now what we have to do as per our module, we have to define the assembly, which is already being done. If let's say if you want to put on some other things, just use this create instance option. Here you can bring the dependent and independent mesh. So whenever I talk about the instances, so make sure dependent mesh means, let's say if you have, I mean, what does that actually means is if you try to bring your geometry and try to understand, like if you have to do the mesh on one part and that is related to a whole assembly, then you can use a dependent part. Independent means, let's say uh, if you want to mesh like 100 bolts, each and everyone has to have a different mesh, then this is where you choose an independent mesh. But let's say if you have 100 bolts but all have a similar mesh, then try to choose like dependent. In that case, you don't have to mesh each and every bolts, only have to mesh one, and everything will be get updated. So this is what exactly how we decide which one do we choose an internal. So for us, it's a dependent mesh again, but we have a 3 unique parts, so it doesn't matter to us. Now the important part is to define the step. So what exactly is the step? Step is simply a sequence of series that you want to perform within your analysis. What exactly we have to do in this part? We have to do like 3 things. Like whatsoever the interferences that we can see right now here, the rubber part, we have to tell to the at the initialization that try to ignore it. That's the frictionless stuff right now. And after that, we have to change the friction, that we involve the friction while pushing, and then we have to apply a plunger displacement, or so-called the force in general. So you can apply a load in 2 terms. One is the load, applying the force, or applying the displacement. So in this case, we will apply the displacement in general. So I hope like you guys have understood how like exactly the steps are defined. So the first step that I want to define is related to the interference, the initial interference, frictionless, and that's a static journal. That's what we are dealing. So make sure when we have to apply the nonlinear geometry is like when we have material given as again nonlinear and we have higher strains. Incrementation, this is what like we have to define like how this particular step is going to run at particular what increments. So it's good enough. Now we define another step. So we want interference where we initiate the friction. So that's another step. And I just want it again 0.1. not a big issue. And the last step that we want is the plunger pull, where we are going to pull the plunger out, and that's going to be again nonlinear, and we want like should be at a really small step so that convergence issue should not come into the action. It's all fine. Now we have all defined the steps, so now it's time to define the interaction. So again, interaction is simply like how you define the material properties. First, like the material, you remember, like initially we defined the material properties, then we assign those properties to the part. Exactly the same we do it for this. We simply go to the interaction. We have interaction properties in this particular module, or you can just define it from here, all the properties, but here you can just directly see it's interaction properties. So you want initially the interference frictionless. I want this to be defined, and so this is a module where we define like the behavior, and so tangential is frictionless, it's all good enough. And normal behavior, how we want the contact algorithm to work. Let's say hard contact, like that we will get to know the penetration effects. I mean, once the part gets touched. Then again, we have to define another one, that is the interference friction. Let's contact again. Again, we have to define the tangential wave, but here we will define the penalty base, and the coefficient of friction is 0.1. And again, the normal behavior hard contact. So we also want the initial initialization, so that the software should know like we have initial interference that has to be ignored. So we have to ignore rather than treat as an interference fits. So it's good enough. So right now we have defined the properties, we have to assign it. So simply just put here. So we want it to be defined like interferences. So make sure like we have to apply this to initial step as a journal contact between each and everything. And we just simply go continue, and what we want is all with self, and we want initiate with the frictionless, and then we want like also the initialization, like there is a treated as a fit, so we just put it here for surface, and this is good enough. Now what we have to do, we have to understand, we have to go to the manager. Interference for the initial discreted for I mean, if I try to make it longer, so initially it is good, like I have a frictionless, but I have defined another property that makes more sense to put it here, modify this particular uh, step like in interference friction to give it like the friction values. So we go to edit and we just change it from here to the friction. That's it. So which means like this is what we have managed, and this is how it's propagated. So if you see again, the friction is added once we are pulling the syringe. So yeah, that's good enough for us. And now interaction is all defined here. We have to define the load. So since we are only working for the displacement boundary condition, so that's what we will define here. So we want to define let's say initial boundary condition. So let's say this part is symmetric. So initially I have to understand like what type of symmetry I have right now here. So here we can see we have Y symmetry as well as the Z symmetry. So accordingly I have to define this boundary conditions. So Y symmetry, and just simply go to the symmetry part. So here also I can say Y symmetry center. Okay, so we have to select it. So what exactly is Y is hold on. Okay, so we select here, we say done. We say it's a by symmetry. That's done. We also have a z symmetry, so we simply go add here the symmetry. So again, going to be at the initial. That's the boundary condition. That's why we just put it, and we can put it here. It's the z symmetry, so we have to select. Hold on. Okay, so this part should be z symmetry. We select here. Okay, and we have to say like symmetry. Okay, so this is what we have defined. Now, what we want is like the barrel. Just this part should be okay. This part should be fixed. So it's a fixture. We again go here. We say the fixed part. Initial fine. We say displacement, and we want this part to be fixed. So it's a fix. So done. We want it to fix in all the directions since it's a solid element, so we don't want rotation even if we're so this is what we did. It's fixed here. Now we want to apply the another load, that is a displacement, to the plunger. So now here what we have to do, we have to couple all the points and try to put a reference point here. So for that, what we have to do, we have to go to the assembly part initially, define the reference point. So this is our reference point here, let's say. I define it. You can also rename it, but it's all up to your call. We have sets, features, and we have features as a reference point. So you can rename it, but it's all fine as of now. And to couple it, we have to go to again to the interaction. Then we have to do, let's say, coupling of all the points with this reference point. Then we have to select the reference point. So this is my reference point. Again, I will search the reference point. It's done. Now I want the surface to be coupled with. So I do coupling, and I want like everything needs to be coupled here. All fine. Now again, I go back to my load case and then define it here like the plunger pull. So I want it to define on the initial, and later I will define the displacement while checking it on the manager. And it's selected here, this one. So RP again, let's see. Okay, so it should be unique. So plunger RP. Now I define it all of them as 0 as the initial, but we know like we can just go to the manager and okay, so y symmetry is not defined correctly, so I need to define y symmetry again. So let's make it an edit, and I guess I have to redefine it on the initial step. So what we can do is we can just delete it here, and we will define it again. But before that, we have to define the plunger pull. So it's propagated. Everything is 0 here. Make sure. But like once we are just starting to pull it, we want it to be not 0, but we want to pull it, correct? So it's minus 25 mm of displacement that I want to put it. So fine. Since I deleted one of the symmetries, so I have to redefine that symmetry again. There's a bisymmetry, so we go here and we write it like symmetry. It's going to be the initial, and we select symmetry, select the regions. Okay, going to be this dot. Okay, well, fine. So we define it here. Now I guess everything is all fine. The only thing left here is the mesh. So we go to the simple part. So orange means like we can not define with the hex mesh. So right now I'm not just going too much deep since our video is going to be a long. I just want to only define the tetra mesh here. So for that, we define it here. We said okay, we are all okay with tetra, and we want it like 2 mm. We apply it here. Say yes, and well, fine. So this is all okay. Barrel. So plunger also again we need to either do the partition to define hexamesh, but I'm okay as of now with the tech mesh. Again, I want to define like 2 mm as a size. Also, make sure like Abacus is a unitless software, so you have to be consistent. If you've decided like with millimeter, I mean, just check it out from your CAD software. Then you have to choose all the dimensions according to that only. This is what is defined here. Into the stopper. Again, either you do partition or simply do the tech mesh. That is okay, 0.5 is small enough, and I say okay. You can also play with this. I mean, let's say if I select, and we can also play with the element type, but as of now, I'm not so much interested into it. So everything is all defined. We have to just submit it, our job, and I will just create it and say like, plunger pull, or we can simply say syringe. So continue. So fine as of now. So probably it's gonna take a bit of time, and we can check it out somehow. We can also alright monitor guys, it. So this is a completed version of that particular example that we did. So what exactly I did, there was some of the error, so I fixed some of the error. So make sure whenever you are trying to run the analysis, you also make add or account those particular errors. So the first and foremost thing was there was a lot of unsymmetricity. So what I did, I just go to this interference frictionless part where we have defined our initial step. So just go to the other, just change the direct. So I mean the solver from the metric storage to the unsymmetric part, so that you know the software can deal with those unsymmetricities and the frictionless issues that we have some initial interference. That's the one of the change I did. And what else you guys can do is like once you're defining, since it's gonna take a bit of your computer hardware capabilities to understand, I mean to check like how good your hardware is while running these analysis. So if you have a really good hardware, then it won't be a big issue. But if you are just uh, within just doing this on your laptop, it's not a desktop, then in that case I believe like try to make those changes. For example, what I did, I just select the part, then I have to select the element type. So the geometric order, I just change it from quadratic. By default it's going to be the quadratic. I change it to the linear part, and that's what I did it for all the part. So that's the second change I did. Also make sure what exactly we want from this particular analysis, the reaction forces, correct? I mean, if we go to the assembly, so we want at reference point the reaction forces, how much force is required to push and pull. So what exactly you have to do, you have to go to the history output. That's what I did it here. So you define a history output, not for the whole model. That's going to be the default. So just define it for a set. That's where like a plunger reference point comes into the action. And we define for every x unit of time for this particular step. If you remember, like we have defined this is the time interval, the time step that we have defined for that plunger pull time step, and output at an approximate times, and just simply go to the reaction forces here. On reaction forces, just understand like this is the free force that we like in the x direction for me, so I've just click it and done it. So that's the three modification I did, and after that everything was all fine, and we got the complete analysis. So we can just check the also the monitor window for your information. So make sure here like three steps are going to be followed. So just first step starts from 0 to 1, then another from 1 to 2, then 2 to 3. So like in 3 steps the analysis got completed. And but also if we check out the results part, so we can check the reaction forces, like here we have defined it, and also like how it goes on. So it was this part. So initially the friction was this was frictionless, then friction comes here, and then the pulling starts. So if I tell you a bit more in details, what happened is like initially initially it was trying to fix the interference, and then if I go more in detail, yeah, so here it just compress it and then it starts pulling it. So that's how like this particular analysis we can check out the visualization. Also if you want to check like the one minus stress, you can check it out where exactly the maximum stress were coming during the analysis. Initially there was no stresses, the frictionless, it tries to pull and then tries to uh, push it backward. Also we can check out the compression pressure for our rubber part, again here. So it first compresses, there is no stresses, and then it goes on and on. So it totally depends on the requirement what exactly you have to do, and you can just plot each and everything. Now what else we have to do, we can also do the plotting. So we define ODB history output. Continue. If you remember, we have defined for the reaction forces 1, RF1. So here it is. So we want to plot it. So this is a reaction forces that we just got it for our analysis. How much force we need to pull the syringe, and also make sure like here it is for quarter part of it. So we have to do the operations here. We can do it in the operate on XY data. So we can just use this data and multiply like 4 times for this particular operation, and we can also plot the expression. So whatever we just get it here is like for the whole syringe, the contact pressure and the reaction force is what we have to define. So that's it. So if you have any other questions, do let me know, and thank you very much for this all.